Imagine you're in a race with a beam of light. You start running, then get in a car, then board a jet, then somehow climb aboard the fastest spacecraft ever built. No matter how fast you go, no matter how much energy you pour into accelerating, that beam of light will always zip away from you at exactly the same speed, 299,792,458 meters per second. Not a meter faster, not a meter slower, always precisely the same. This cosmic speed limit is woven into the very fabric of reality itself, shaping everything from the flow of time to the structure of space, from the smallest subatomic particles to the largest galaxies. If you're curious about these mysteries, make sure to subscribe to this channel and give a thumbs up. I am just starting my journey on YouTube, and your support means a lot to me. One quick question. What's the first question you'd ask an alien civilization if we made contact with them tomorrow? Comment down below. I will choose the most creative answer. Now let's begin. We didn't always know light had a speed. For most of human history, people assumed light traveled instantaneously. When you opened your eyes, you saw everything immediately, right? It wasn't until 1676 that a Danish astronomer named Ole Rømer made a discovery that changed everything. He was studying Jupiter's moon Io, timing its eclipses as it passed behind the giant planet. Rømer noticed something odd. When Earth was moving away from Jupiter in its orbit, Io's eclipses happened slightly later than predicted. When Earth was moving toward Jupiter, they happened slightly earlier. The only explanation that made sense was revolutionary. Light wasn't instantaneous. It took time to travel from Jupiter to Earth, and that time changed as the distance between the planets changed. From these observations, Rømer calculated that light traveled at about 220,000 kilometers per second, remarkably close to the actual value, considering the limited precision of 17th century instruments. For the first time in history, humans realized that light had a finite speed, that there was a cosmic speed limit built into nature itself. But discovering that light had a speed was just the beginning. The real mystery was why it had that particular speed, and why nothing could go faster. That mystery would take another 2 centuries to solve, and the answer would revolutionize our understanding of reality itself. The story truly begins with James Clerk Maxwell in the 1860s. Maxwell was studying electricity and magnetism, two forces that seemed completely different. Electric charges created electric fields, magnets created magnetic fields, and while there were some connections between them, nobody understood the deep relationship that united them. Maxwell's genius was in expressing these phenomena as mathematical equations, 4 beautiful equations that described everything about electricity and magnetism. But when he manipulated these equations, something extraordinary emerged. The equations predicted that changing electric fields would create magnetic fields, and changing magnetic fields would create electric fields. These fields could propagate through space as waves, feeding off each other, traveling at a very specific speed. When Maxwell calculated this speed, he got a shock. The speed of these electromagnetic waves was exactly the speed of light that had been measured by increasingly precise experiments. This couldn't be a coincidence. Maxwell had discovered that light itself was an electromagnetic wave, a dance of electric and magnetic fields propagating through space. But Maxwell's equations revealed something even more profound. The speed of light emerged naturally from the fundamental properties of space itself, specifically from 2 constants called the permittivity and permeability of free space. These weren't arbitrary numbers, they described how space itself responded to electric and magnetic fields. The speed of light was literally built into the fabric of empty space. This created a paradox that would torment physicists for decades. Maxwell's equations said that light always traveled at the same speed, but they didn't say relative to what. In everyday experience, speeds are always relative. If you're on a train moving at 100 kilometers per hour and you walk forward at 5 kilometers per hour, you're moving at 105 kilometers per hour relative to the ground. But Maxwell's equations seem to say that light didn't follow this rule. Scientists proposed that light waves, like sound waves or water waves, must travel through some medium. They called this hypothetical medium the luminiferous ether, a substance that filled all of space, providing something for light waves to wave through. The speed of light, they reasoned, must be relative to this cosmic ether. In 1887, Albert Michelson and Edward Morley performed one of the most famous experiments in physics history. Using an incredibly sensitive device called an interferometer, they tried to detect Earth's motion through the ether. As Earth orbited the Sun at 30 kilometers per second, we should be moving through the ether, creating an ether wind. That would affect the speed of light in different directions. The experiment was a spectacular failure, or rather a spectacular success, depending on how you look at it. No matter which direction they measured, no matter what time of year, light always traveled at exactly the same speed. There was no ether wind. Light's speed was somehow absolute, the same for all observers regardless of their motion. This null result sent shockwaves through the physics community. How could light always travel at the same speed for everyone? It violated common sense and everything physicists thought they knew about motion. Various explanations were proposed, including the idea that the ether was somehow dragged along by Earth, but none of them really worked. The resolution would come from a young patent clerk in Switzerland who was willing to think the unthinkable. In 1905, Albert Einstein published his special theory of relativity, built on two simple but radical postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is the same for all observers, regardless of their motion. Speaking of mind-bending physics and the mysteries of time, if you've ever wondered what would actually happen to your body and mind if you could somehow travel at the speed of light, I explored that incredible journey in my video called "What Would Really Happen If You Traveled at Light Speed?" The reality is far stranger than any science fiction. Check out, after this video, the link is in the description and card above. Now back to our journey. These simple statements led to consequences that shattered our intuitive understanding of reality. If light's speed is constant for everyone, then space and time themselves must be flexible. Moving clocks run slow, moving objects contract in length. Mass and energy are equivalent, related by the famous equation E equals mc squared. The faster you go, the more these effects become apparent, and as you approach the speed of light, they become extreme. But why? Why does the universe work this way? The answer lies in a deeper understanding of what space and time actually are. Einstein's former mathematics professor, Hermann Minkowski, provided the key insight in 1908. He showed that space and time aren't separate entities, but are woven together into a four-dimensional fabric called spacetime. In Minkowski's revolutionary vision, the speed of light isn't really about light at all. It's about the fundamental structure of spacetime itself. Imagine spacetime as a vast fabric with 3 dimensions of space and 1 of time woven together inseparably. The speed of light is the conversion factor between space and time, the cosmic exchange rate that tells us how much space equals how much time. This isn't just abstract mathematics, it's the actual architecture of reality. When you sit still, you're moving through time at maximum speed, 1 second per second. But when you move through space, some of your motion through time gets diverted into motion through space. The faster you move through space, the slower you move through time. And there's a maximum speed at which you can move through space. the speed where all your motion through time has been converted to motion through space. That speed is the speed of light. Think about what this means. You're always moving through space-time at the speed of light. Always. Right now, sitting still, you're racing through time at light speed. When you get up and walk, you're diverting a tiny fraction of that motion into movement through space. If you could somehow reach light speed through space, you'd stop moving through time entirely. This is why photons, particles of light, don't experience time. From a photon's perspective, its emission and absorption happen simultaneously, even if it travels billions of light years. This profound insight explains why nothing can exceed light speed. It's not that there's some cosmic police force preventing it. It's that light speed is the total speed through space-time, and you can't go faster than your total speed. It would be like trying to go north from the North Pole. The question doesn't even make sense within the geometry of reality. Dr. Brian Cox at the University of Manchester often demonstrates this with a beautiful analogy. Imagine you're on a train heading northeast at 100 kilometers per hour. Your total speed is 100 kilometers per hour, but it's divided between northward and eastward motion. You could change direction to go more north and less east, or more east and less north, but your total speed remains 100 kilometers per hour. Similarly, in space-time you can trade motion through time for motion through space, but your total speed through space-time remains constant, the speed of light. But the story gets even more fascinating when we consider what happens as you approach light speed. According to Einstein's equations, as you accelerate, several remarkable things happen. Your mass effectively increases, requiring more and more energy to accelerate further. Time dilation becomes extreme. Clocks on your spaceship run slower compared to clocks on Earth. Length contraction squeezes space in your direction of travel. These aren't illusions or measurement errors, they're real physical effects arising from the geometry of space-time. The Large Hadron Collider at CERN provides daily confirmation of these effects. Protons are accelerated to 99.999991% of light speed. That's 7 nines after the decimal point. At this speed, the proton's effective mass increases by a factor of 7,000. That's why the LHC needs such enormous energies to push particles so close to light speed. It's not fighting friction or air resistance, it's fighting the fundamental geometry of space-time itself. Time dilation at these speeds is equally extreme. Unstable particles called muons are created when cosmic rays hit Earth's upper atmosphere. Muons only live for 2.2 microseconds before decaying, which should mean they travel only 660 meters before vanishing. Yet we detect muons at sea level, having traveled over 10 kilometers through the atmosphere. How? From our perspective, time dilation extends their lifespan. From the muon's perspective, length contraction shrinks the atmosphere. Both viewpoints are equally valid and lead to the same result, a beautiful confirmation of Einstein's theory. GPS satellites provide a more everyday example of these effects. These satellites orbit Earth at about 14,000 kilometers per hour, fast enough that time dilation causes their clocks to run 7 microseconds per day, slower than Earth clocks. But they're also higher in Earth's gravitational field, which causes their clocks to run 45 microseconds per day faster. The net effect, 38 microseconds per day, might seem tiny, but GPS requires nanosecond precision. Without correcting for relativistic effects, GPS would accumulate errors of about 10 kilometers per day. But why does mass increase as you approach light speed? This brings us to one of the most profound insights in physics. Mass is really just confined energy. Einstein's famous equation, E equals mc squared, tells us that mass and energy are different forms of the same thing. The m in the equation isn't just the rest mass, it's the total mass, including the kinetic energy of motion. As you accelerate, you're adding kinetic energy to an object. But energy has mass, that's what E equals mc squared means. So adding energy means adding mass, which means you need even more force to continue accelerating. As you approach light speed, the energy required approaches infinity. You'd need infinite energy to reach light speed, which is obviously impossible. Dr. Lisa Randall at Harvard University has pointed out that this speed limit is actually a feature, not a bug. If there were no cosmic speed limit, causality itself would break down. You could send signals into your own past, creating grandfather paradoxes and logical contradictions. The speed of light maintains the logical consistency of the universe, ensuring that causes always precede effects. This connection between light speed and causality becomes clear when you draw spacetime diagrams. These diagrams, invented by Minkowski, show time on the vertical axis and space on the horizontal axis. Light travels at 45-degree angles on these diagrams, creating light cones that divide spacetime into regions. Your future light cone contains all the events you could possibly influence. Your past light cone contains all the events that could have influenced you. Events outside your light cones are causally disconnected from you. They can neither affect you nor be affected by you. This isn't just theoretical. Astronomers use light cones every day. When we observe a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. When we're looking into our past light cone, that galaxy's present is outside our light cone, causally disconnected from us. We can't know what it looks like now because now depends on your reference frame. Another consequence of relativity. The Laser Interferometer, Gravitational Wave Observatory, LIGO, has provided stunning confirmation of how the speed of light governs even gravity itself. When LIGO detected gravitational waves from colliding black holes, the waves arrived at precisely the moment expected if gravity travels at light speed. This was a crucial test. Einstein's theory predicted that gravitational effects propagate at light speed, not instantaneously as Newton had assumed. In 2017, LIGO and the Virgo detector observed both gravitational waves and light from the same event. Two neutron stars colliding 130 million light-years away. The gravitational waves and gamma rays arrived within 1.7 seconds of each other after traveling for 130 million years. This incredible precision confirmed that gravity and light travel at the same speed, further evidence that light speed is fundamental to the structure of spacetime itself. But there's an even deeper reason why light has this particular speed, and it has to do with the quantum nature of reality. In quantum field theory, every particle is an excitation in a quantum field that fills all of space. The photon is an excitation in the electromagnetic field. The electron is an excitation in the electron field. These fields can interact and exchange energy, but they do so through virtual particles that pop in and out of existence. The quantum field theory picture reveals something extraordinary. The speed of light emerges from the most fundamental level of reality. In this framework, empty space isn't empty at all. It's a seething ocean of virtual particles constantly appearing and disappearing, borrowing energy from the vacuum and paying it back before the universe notices. This quantum foam, as physicist John Wheeler called it, operates at scales so small and time so brief that we can't directly observe it, yet its effects shape everything we see. Dr. Frank Wilczek, who won the Nobel Prize for his work on the strong force, describes the vacuum as a kind of cosmic superconductor. Just as electrons flow through a superconductor without resistance, particles move through the quantum vacuum following specific rules. The speed of light represents the maximum rate at which disturbances can propagate through this quantum medium, not because of any mechanical limitation, but because of the fundamental quantum relationships between space, time, and energy. This becomes clearer when we consider what physicists call the uncertainty principle. discovered by Werner Heisenberg in 1927. This principle states that you can't simultaneously know both the exact position and momentum of a particle, but it goes deeper. It also relates energy and time. The more precisely you try to measure energy, the longer it takes. The shorter the time interval, the more uncertain the energy becomes. This uncertainty allows virtual particles to pop into existence, borrowing energy from the vacuum as long as they pay it back quickly enough. The more energy they borrow, the faster they must repay it. This creates a fundamental relationship between energy, distance, and time that ultimately gives rise to the speed of light. Virtual photons, the carriers of electromagnetic force, can only travel a certain distance before they must disappear, and this maximum distance divided by the minimum time gives us light speed. Recent experiments at the SLAC National Accelerator Laboratory have pushed our understanding of these quantum effects to new extremes. By colliding electrons with intense laser beams, scientists have observed the creation of matter-antimatter pairs from pure light, a process called the Bright-Wheeler process, predicted in 1934, but only recently confirmed. These experiments show that even empty space, when pumped with enough energy, reveals its quantum nature and confirms that mass, energy, and light speed are intimately connected at the quantum level. But here's where things get really mind-bending. The speed of light might not be as constant as we thought, at least not over cosmic time. Dr. Joan Magacho at Imperial College London and Dr. Andreas Albrecht have proposed that light speed might have been different in the early universe. This variable speed of light theory could solve several cosmological puzzles, including why the universe appears so uniform on large scales. The idea isn't as crazy as it sounds. We know that other constants of nature might not be truly constant. Observations of distant quasars by the Very Large Telescope in Chile have found hints that the fine structure constant, which determines the strength of electromagnetic interactions, might have been slightly different billions of years ago. If this constant can change, why not the speed of light? Dr. John Webb at the University of New South Wales has led efforts to measure these potential variations using the light from distant galaxies. By analyzing how atoms in these galaxies absorb light, his team can measure physical constants as they were billions of years ago. While the results remain controversial, they've found tantalizing hints that fundamental constants might vary across space and time, suggesting our universe might be even stranger than we imagined. This brings us to one of the most profound questions in physics. Why does light have this particular speed? Why 299,792,458 meters per second and not some other value? The answer might lie in the anthropic principle, the idea that physical constants have the values they do, because otherwise we wouldn't be here to observe them. If light speed were significantly different, the universe would be unrecognizable. A much faster light speed would mean weaker electromagnetic forces making atoms unstable. A much slower light speed would mean stronger forces preventing complex chemistry. The fine-tuning of light speed, along with other constants, seems almost miraculous, unless our universe is one of countless others with different values, and we naturally find ourselves in one compatible with our existence. The multiverse theory, supported by many physicists, including Dr. Max Tegmark at MIT, suggests that different regions of a larger reality might have different physical constants, including different light speeds. In this view, the speed of light in our universe isn't special or designed. It's just one value among many, and we observe this particular value because it allows atoms, stars, planets, and life to exist. But the speed of light limit has even stranger implications when we consider quantum entanglement. When two particles become entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments have confirmed that entanglement is real, and the correlation between entangled particles appears to be instantaneous. Does this violate the speed of light limit? Not quite. Dr. Nicholas Gissin at the University of Geneva has shown that while entangled particles are correlated instantly, you can't use entanglement to send information faster than light. The results of measurements on entangled particles are random. Only when you compare results afterward, at light speed or slower, do you see the correlation. Quantum mechanics respects the light speed limit in a subtle way, preserving causality while allowing for non-local connections. Recent experiments have pushed quantum entanglement to extraordinary scales. Chinese scientists using the Messius quantum satellite have demonstrated entanglement between particles separated by over 1,200 kilometers. The European Space Agency is planning even more ambitious experiments that could test entanglement across millions of kilometers. These experiments probe whether the light speed limit applies to quantum correlations in the same way it applies to classical information. The holographic principle, developed by physicists like Dr. Gerard 't Hooft and Dr. Leonard Susskind, suggests an even deeper connection between information and the speed of light. This principle states that all the information in a volume of space can be encoded on its boundary, like a hologram. The maximum amount of information that can fit in a region is proportional to its surface area, not its volume, and this limit is directly related to the speed of light and the fundamental quantum unit of area. This has led to a profound insight. The speed of light might be fundamentally about information. Dr. Juan Maldacena's ADS CFT correspondence shows that a gravitational theory in a volume can be exactly equivalent to a quantum theory on its boundary. In this picture, the speed of light in the bulk emerges from the properties of entanglement on the boundary. Space, time, and the speed of light might all be emergent properties of a more fundamental information-theoretic reality. The black hole information paradox highlights these deep connections. When matter falls into a black hole, information about its quantum state seems to be destroyed when the black hole evaporates through Hawking radiation. But quantum mechanics says information must be preserved. Recent theoretical breakthroughs suggest that information is somehow encoded in subtle correlations in the radiation, preserving unitarity but in a highly scrambled form. The speed of light plays a crucial role in how quickly information can be scrambled and retrieved from black holes. Dr. Daniel Harlow at MIT and Dr. Patrick Hayden have shown that black holes are the fastest scramblers of information allowed by physics, processing information at the maximum rate permitted by the speed of light limit. This isn't coincidence. It reflects deep connections between gravity, quantum mechanics, information theory, and the structure of space-time itself. The speed of light doesn't just limit how fast we can travel. It fundamentally shapes what we can know about the universe. Because light takes time to reach us, we never see the universe as it is now. We see it as it was. The farther we look into space, the further we look back in time. This creates what astronomers call the observable universe, a sphere centered on Earth containing everything whose light has had time to reach us since the Big Bang 13.8 billion years ago. But here's what will blow your mind. The observable universe is much larger than 13.8 billion light-years across. Due to the expansion of space, the most distant galaxies we can see are now about 46 billion light-years away. Their light has been traveling toward us for most of the universe's history, but during that time, space itself has been stretching, carrying those galaxies even farther away. We see them as they were billions of years ago when they were much closer, but we know from the cosmological redshift that they're now vastly more distant. Dr. Max Tegmark at MIT has calculated that the observable universe contains roughly 2 trillion galaxies, each containing hundreds of billions of stars. But this is just a tiny fraction of what exists. Beyond our cosmic horizon lies potentially infinite space filled with galaxies we'll never see. The speed of light creates an absolute boundary to our knowledge, a cosmic horizon beyond which we cannot observe, no matter how powerful our telescopes become. This cosmic horizon isn't static, it's growing. Every second, light from slightly more distant regions reaches us for the first time, expanding our observable universe by about 1 light second in radius. But paradoxically, we're also losing access to galaxies. Due to dark energy accelerating cosmic expansion, galaxies are disappearing beyond a different horizon, the event horizon of the observable universe. Once they cross this boundary, their light will never reach us, no matter how long we wait. Dr. Lawrence Krauss at Arizona State University has calculated that in about 100 billion years, all galaxies beyond our local group will have vanished beyond this cosmic event horizon. Future civilizations will see a universe containing only the merged remnant of the Milky Way and Andromeda galaxies, surrounded by absolute darkness. They'll have no way to discover the Big Bang or learn about cosmic expansion. The speed of light, combined with accelerating expansion, will have erased the evidence of the universe's history. But the speed of light creates horizons in time as well as space. When we observe the cosmic microwave background radiation with satellites like Planck and WMAP, we're seeing light that has been traveling since the universe became transparent, about 380,000 years after the Big Bang. This creates a temporal horizon we cannot see earlier times through electromagnetic radiation because the universe was opaque to light. The James Webb Space Telescope, launched in 2021, is pushing our observations closer to this fundamental limit. It has detected galaxies that existed just a few 100 million years after the Big Bang. Their light redshifted so severely that what was once visible light now arrives as infrared radiation. These observations are revealing that galaxies formed earlier and faster than our models predicted, forcing us to revise our understanding of cosmic evolution. But here's where the story takes an incredible turn. While we can't see beyond the cosmic microwave background with light, we can potentially observe even earlier times using gravitational waves. These ripples in space-time travel at light speed, but can propagate through the dense early universe that was opaque to electromagnetic radiation. Future gravitational wave detectors might observe signals from the first fraction of a second after the Big Bang, carrying information about quantum gravity and the birth of space-time itself. The speed of light also shapes the universe's structure on the largest scales. Observations by the Sloan Digital Sky Survey have mapped millions of galaxies, revealing that they're not randomly distributed, but form a cosmic web. Vast filaments of galaxies separated by enormous voids. The size of these structures is limited by the speed of light. Since gravity also propagates at light speed, structures can only grow as large as gravity has had time to pull matter together since the Big Bang. Dr. Margaret Geller at the Harvard-Smithsonian Center for Astrophysics, who co-discovered this cosmic web structure, has shown that the largest structures in the universe are about 1 billion light-years across. Anything larger would require gravitational influences to have traveled faster than light, which is impossible. The speed of light literally determines the maximum size of cosmic structures. This brings us to one of the most profound realizations about our universe. We live in a cosmic speed trap. The speed of light is slow compared to the vast distances between stars and galaxies. It takes light 4.2 years to reach the nearest star, 2.5 million years to reach the nearest large galaxy, and billions of years to cross the observable universe. This cosmic speed limit has profound implications for life and intelligence in the universe. Consider what this means for interstellar communication. If we detected a signal from a civilization orbiting Proxima Centauri, our nearest stellar neighbor, any conversation would take 8.4 years per exchange, 4.2 years for our message to reach them, and 4.2 years for their reply to return. For more distant civilizations, the communication delays become impractical. A conversation with a civilization in the Andromeda Galaxy would take 5 million years per exchange. This cosmic isolation might explain the Fermi paradox. If the universe is filled with life, why haven't we encountered any evidence of it? Dr. Robin Hanson has proposed that the speed of light creates isolated islands of intelligence in a vast cosmic ocean. Civilizations might be common, but the light speed barrier keeps them forever separated, unable to form a true galactic community. But there's an even deeper way that light's speed limit shapes reality. The finite speed of light, combined with quantum mechanics, leads to one of the most successful theories in physics, quantum field theory. This framework describes particles as excitations in quantum fields that fill all of space. The speed of light appears naturally in these theories as the maximum speed at which field disturbances can propagate. And if you're fascinated by how light's speed shapes everything from quantum fields to the structure of reality, I highly recommend the book called Light, A Radiant History from Creation to the Quantum Age by Bruce Watson. This book isn't just about the science. It's a captivating journey through the history, culture, and breakthroughs that have shaped our understanding of light, from ancient myths to Einstein and quantum physics. Watson weaves together stories of discovery, the mysteries of light speed, and the scientists who changed how we see the universe. If you want to truly appreciate why light is so central to everything in physics, this is the perfect next read. You'll find the book in the link in the description. Dr. Richard Feynman, one of the architects of quantum field theory, showed that the electromagnetic force between charged particles arises from the exchange of virtual photons. These photons can briefly violate energy conservation thanks to quantum uncertainty, but they must do so within limits set by the speed of light. The entire structure of electromagnetic interactions, and by extension, all of chemistry and biology, depends on light having a finite speed. Recent experiments at the Large Hadron Collider have probed these quantum field effects at unprecedented energies. When protons collide at nearly light speed, they create a soup of quarks and gluons that briefly reproduces conditions from microseconds after the Big Bang. The behavior of this quark-gluon plasma confirms our understanding of how quantum fields behave near the speed of light limit. But perhaps the most mind-bending aspect of light's speed limit is what it tells us about the nature of time itself. In relativity, time isn't universal, it's personal. Each observer carries their own time, their own now, and these can disagree dramatically depending on relative motion. The speed of light is what relates one observer's time to another's, providing the conversion factor between different temporal perspectives. Dr. Carlo Rovelli, one of the founders of loop quantum gravity, has argued that time might not be fundamental at all. In his view, time emerges from the relationships between physical systems, and the speed of light governs how these relationships can change. At the deepest level of reality, there might be no time, only relationships that change according to rules that give rise to what we perceive as temporal flow. This perspective is supported by studies of black holes, where time behaves in extreme ways. Near a black hole's event horizon, gravitational time dilation becomes so severe that time nearly stops relative to distant observers. For someone falling into a black hole, they experience normal time right up to crossing the event horizon. But from outside, we would see them slow down and freeze at the horizon, their final photons redshifted to infinity by the extreme warping of spacetime. Throughout our exploration of light's cosmic speed limit, you might be wondering, is there really no way around it? Are we forever trapped by this universal restriction? The answer is both yes and no. While special relativity absolutely forbids traveling through space faster than light, general relativity, Einstein's theory of gravity, opens up tantalizing possibilities that don't violate the cosmic speed limit but might achieve the same result through cosmic cleverness. The first loophole comes from the very nature of spacetime itself. While nothing can move through space faster than light, space itself has no such restriction. During cosmic inflation, the universe expanded by a factor of at least 10 to the 26, in about 10 to the negative 32 seconds, an expansion rate that far exceeded light speed. This wasn't a violation because it was space itself expanding, carrying matter along for the ride, like raisins in rising bread dough. Dr. Miguel Alcubierre at the National Autonomous University of Mexico realized in 1994 that this principle could theoretically enable faster-than-light travel. His proposed warp drive would contract space in front of a spacecraft and expand it behind, creating a bubble that surfs through space-time. Inside the bubble, the spacecraft never exceeds light speed relative to its local space. It's the bubble itself that moves faster than light by warping the geometry of space-time. The mathematics of the Alcubierre drive is solid. It's a valid solution to Einstein's field equations. The problem is the requirements. Initial calculations suggested you'd need exotic matter with negative energy density equivalent to the mass energy of Jupiter. Dr. Harold White at NASA's Johnson Space Center has refined these calculations, reducing the energy requirements dramatically by optimizing the warp bubble's shape, but we're still talking about energies far beyond current technology. Even more challenging is the requirement for exotic matter, stuff with negative energy density that creates repulsive gravity. While we've never observed such matter in bulk, quantum physics suggests it might exist. The Casimir effect, where quantum vacuum fluctuations between closely spaced metal plates create negative energy density, proves that exotic matter is theoretically possible. But scaling this up from microscopic quantum effects to macroscopic warp drives remains a formidable challenge. Wormholes offer another potential loophole. These theoretical shortcuts through space-time, first discovered in Einstein's equations by Ludwig Flamm in 1916, could connect distant regions of space like cosmic subway tunnels. If wormholes exist and could be traversed, you could travel between stars without ever exceeding light speed locally. You'd just be taking a shortcut through a higher dimension. Dr. Kip Thorne at Caltech, working with his students, showed in the 1980s that traversable wormholes are theoretically possible, but would require exotic matter to keep them open. Without it, any wormhole would collapse faster than light could traverse it. Thorne's work wasn't just theoretical speculation. He was consulting for Carl Sagan's novel Contact and wanted to provide scientifically plausible faster-than-light travel. Recent theoretical work has suggested more exotic possibilities. Dr. Juan Maldacena and Dr. Leonard Susskind have proposed that quantum entanglement and wormholes might be fundamentally the same phenomenon, that entangled particles are connected by microscopic wormholes. If true, this ER equals EPR conjecture would unite quantum mechanics and general relativity in a profound way, suggesting that space itself might be woven from quantum entanglement. But even if we can't travel faster than light, the universe offers a consolation prize: time dilation. As you approach light speed, time slows down for you relative to the rest of the universe. At 90% light speed, time passes at about half the normal rate. At 99.9%, it's slowed by a factor of 22. At speeds achievable by cosmic ray particles, 99.9999% of light speed, millions of years pass in the outside universe for every second of traveler time. This relativistic time dilation isn't science fiction. It's observed daily in particle accelerators and cosmic ray detectors. The Oh My God particle, detected in 1991, was a cosmic ray proton traveling so close to light speed that it experienced the 200,000 light-year journey across our galaxy in just 20 seconds of its own time. From our perspective, it traveled for 200,000 years. From its perspective, the galaxy was length contracted to just 6 light seconds across. Dr. Avi Loeb at Harvard has calculated that with constant 1g acceleration, comfortable for human travelers, you could reach the center of our galaxy in 20 years of ship time, though 40,000 years would pass on Earth. You could reach the Andromeda galaxy in 28 years of ship time, while Earth experienced 2 million years. In principle, you could explore the entire observable universe within a human lifetime, though you'd return to find the sun long dead and humanity either extinct or evolved beyond recognition. Quantum mechanics offers its own peculiar relationship with light speed. Quantum tunneling allows particles to seemingly teleport through barriers instantly, appearing on the other side without crossing the intervening space. Recent experiments at the University of Toronto measured electrons tunneling through barriers and found the process takes 0 time. It's truly instantaneous. Yet this doesn't violate relativity because you can't control which particles tunnel or when, preventing faster-than-light communication. The quantum Zeno effect provides another strange phenomenon. By repeatedly measuring a quantum system, you can freeze its evolution, preventing radioactive decay or other quantum transitions. In 2015, researchers at Cornell University used this effect to freeze atoms in place for several seconds, an eternity in quantum terms. While this doesn't enable faster-than-light travel, it shows how quantum mechanics can manipulate time in ways that classical physics never imagined. Dr. Günter Nimtz at the University of Cologne has conducted controversial experiments suggesting that quantum tunneling might enable faster-than-light signaling. His experiments with microwaves tunneling through barriers showed the peak of the wave packet arriving faster than light speed would allow. While most physicists believe this doesn't constitute true faster-than-light information transfer, the debate highlights how quantum mechanics pushes against relativistic limits in subtle ways. Even more exotic is the possibility of tachyons, hypothetical particles that always travel faster than light. While never observed, tachyons are mathematically consistent with relativity, though they would have imaginary mass and experience time backward. Dr. Gerald Feinberg, who coined the term in 1967, showed that tachyons wouldn't violate relativity if they couldn't slow down to light speed, just as ordinary matter can't speed up to it. The search for tachyons has yielded null results, but their theoretical possibility reminds us that our universe might contain phenomena beyond current physics. Neutrinos were once thought to be tachyons when early experiments incorrectly measured them traveling faster than light. While those measurements were eventually corrected, they sparked serious theoretical work on what faster-than-light particles would mean for causality and physics. String theory, our best candidate for quantum gravity, suggests even more radical possibilities. Extra dimensions beyond our familiar 3 could provide shortcuts through higher dimensional space. Dr. Lisa Randall at Harvard has proposed that our universe might be a 3-dimensional brain embedded in a higher dimensional bulk. While we're confined to our brain, gravity might leak into the bulk, and advanced civilizations might find ways to access these extra dimensions. Recent observations have placed strict limits on extra dimensions, but they could still exist if they're either very small or very large. The Large Hadron Collider searches for signs of extra dimensions by looking for missing energy that might have escaped into them. While no evidence has been found yet, the search continues at ever higher energies. As we delve deeper into the nature of light's speed limit, we encounter one of the most profound mysteries in modern physics, the relationship between information, consciousness, and the cosmic speed limit. You see, the speed of light isn't just about how fast things can move, it's fundamentally about how fast information can propagate through the universe. And this connection reveals deep truths about the nature of reality itself. Information, in the physics sense, isn't just data or knowledge, it's the fundamental currency of reality. Every particle carries information about its quantum state. Every interaction exchanges information between systems, and crucially, this information cannot travel faster than light. This isn't just a practical limitation, it's what preserves causality and prevents paradoxes that would make the universe logically inconsistent. Dr. Rolf Landauer at IBM made a revolutionary discovery in 1961. Information is physical. Erasing one bit of information necessarily releases heat, establishing a fundamental connection between information theory and thermodynamics. This principle, now called Landauer's principle, shows that information processing has physical consequences that must respect the laws of physics, including the speed of light. This becomes particularly dramatic when we consider black holes. When matter falls into a black hole, what happens to its information? Stephen Hawking's discovery that black holes evaporate through quantum radiation created a paradox. The radiation appears to be random thermal emission, containing no information about what fell in, but quantum mechanics says information must be preserved. This conflict between general relativity and quantum mechanics has driven decades of research. Recent breakthroughs suggest the resolution might involve the speed of light in subtle ways. Dr. Leonard Suskind's principle of black hole complementarity proposes that information can exist in two places at once, both falling into the black hole and encoded on its surface. But the speed of light prevents any observer from seeing both copies. The information is preserved, but in a way that respects relativistic limits. The holographic principle, developed by Dr. Gerard 't Hooft and refined by Suskind, takes this further. It suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. The maximum information content of any region is proportional to its surface area, not its volume, and this limit is directly related to the speed of light and the Planck scale. In essence, the speed of light determines how much information can exist in any region of space. Dr. Juan Maldacena's ADS-CFT correspondence provides concrete mathematical evidence for this principle. He showed that a gravitational theory in a volume is exactly equivalent to a quantum field theory on its boundary. Information in the bulk spacetime is encoded in entanglement patterns on the boundary. The speed of light in the bulk emerges from the structure of entanglement on the boundary. Space, time, and light speed are all emergent from more fundamental information theoretic principles. This brings us to quantum entanglement and its mysterious relationship with light speed. When particles become entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and believed it showed quantum mechanics was incomplete. But experiments have confirmed entanglement is real, and the correlations appear instantaneous. In 2015, researchers at Delft University of Technology performed a loophole-free test of quantum entanglement, closing all the experimental gaps that skeptics had identified. They showed that entangled particles separated by 1.3 kilometers exhibited correlations that would require signals traveling at least 10,000 times light speed to explain classically. Yet this doesn't enable faster-than-light communication because the measurement results are random. Only the correlations are non-local. Dr. Nicholas Gissin at the University of Geneva has pushed these experiments to extraordinary scales. His team has demonstrated entanglement through optical fibers over distances exceeding 100 kilometers. The correlations remain perfect, showing no delay that would indicate a finite propagation speed. If entanglement correlations propagate at finite speed, it must be at least 10 million times light speed, effectively instantaneous. But here's the crucial point. While entanglement correlations appear instantaneous, you cannot use them to send information faster than light. The no communication theorem, proven mathematically, shows that entanglement alone cannot transmit messages. The randomness of quantum measurements ensures that any attempt to encode information in entangled states fails. The universe seems carefully designed to allow non-local correlations while preserving the light speed limit on information transfer. This leads to profound questions about consciousness and observation. In quantum mechanics, observation causes wave function collapse, the transition from quantum superposition to definite states. But what constitutes an observation? Does it require consciousness? And how does the speed of light limit apply to the seemingly instantaneous collapse of extended wave functions? Dr. Roger Penrose at Oxford has proposed that consciousness itself might be fundamentally connected to quantum gravity and the speed of light. His orchestrated objective reduction theory suggests that consciousness arises when quantum superpositions in brain microtubules reach a threshold related to gravitational effects. The collapse time depends on the mass energy involved and Planck scale physics, where quantum mechanics meets relativity at light speed. Recent neuroscience research has found intriguing connections between brain activity and relativistic physics. Dr. Vitaly Vanchurin at the University of Minnesota has proposed that neural networks naturally implement a kind of relativistic computation, with the speed of neural signals playing a role analogous to light speed in creating a personal now for conscious experience. The finite speed of neural transmission might be essential for creating the unified conscious experience from distributed brain activity. The Global Consciousness Project, running since 1998, has collected data suggesting that human consciousness might have subtle, non-local effects. Random number generators around the world show small but statistically significant deviations during major global events. While controversial, these results hint at connections between consciousness and physical processes that we don't yet understand. Dr. Stuart Hameroff at the University of Arizona, collaborating with Penrose, has suggested that consciousness might involve quantum processes that push against the limits of classical spacetime. If consciousness can access quantum information in ways that classical systems cannot, it might experience aspects of reality that transcend normal spacetime limitations, while still respecting the fundamental speed of light limit. The relationship between information, consciousness, and light speed becomes even more intriguing when we consider artificial intelligence. As we build increasingly sophisticated information processing systems, we're essentially creating new forms of consciousness, or at least intelligence. These systems must respect the speed of light, which limits how fast they can process information and how large they can grow while maintaining coherent operation. Dr. Anders Sandberg at Oxford's Future of Humanity Institute has calculated fundamental limits on computation imposed by physics. The speed of light limits how fast information can move between parts of a computer, ultimately constraining processing speed. A computer the size of Earth would face nanosecond delays between opposite sides. A galaxy-spanning intelligence would face 100,000-year delays, making coherent thought impossible without some form of faster-than-light communication. This might explain why we don't see evidence of galaxy-spanning superintelligences despite the age of the universe. The speed of light doesn't just limit travel and communication, it limits the maximum size of coherent intelligence. Any sufficiently large intelligence would fragment into smaller, light-speed-limited domains, unable to maintain unified consciousness across cosmic distances. But quantum computing offers intriguing possibilities. By exploiting quantum superposition and entanglement, quantum computers can explore multiple solution paths simultaneously. While they still can't send information faster than light, they can process certain types of information exponentially faster than classical computers. As we develop more powerful quantum computers, we're essentially learning to compute with the same principles the universe uses at its fundamental level. As we approach the deeper truth about light's speed limit, we must confront a startling realization. The universe seems almost conspiratorially designed to enforce this cosmic speed limit. It's not just one law or principle that creates this barrier. It's a convergence of physics at every level, from quantum mechanics to cosmology, all working together to maintain this fundamental restriction. The question isn't just why light has a speed limit, but why the universe seems so determined to preserve it. Dr. Lee Smolin at the Perimeter Institute has argued that the laws of physics might have evolved through a process of cosmological natural selection. In his theory, universes that create black holes spawn new universes with slightly different physical constants. Over cosmic time, this would lead to universes fine-tuned to produce black holes enough, and coincidentally, the conditions necessary for stars, planets, and life. The speed of light might be optimized through this cosmic evolution. This evolutionary view gains support from the remarkable coincidences in physics. The speed of light, Planck's constant, and Newton's gravitational constant combine to create natural units of length, time, and mass, the Planck units. These aren't arbitrary human constructs, but emerge from the fundamental structure of physics. At the Planck scale, quantum mechanics and gravity become equally important, suggesting this is the fundamental grain of reality. Dr. John Barrow at Cambridge University has shown that the speed of light plays a crucial role in making the universe habitable. If light speed were significantly different, the fundamental forces would be thrown out of balance. Electromagnetic forces would be too strong or too weak for stable atoms. Nuclear fusion in stars would proceed too fast or too slow. The delicate balance that allows complex chemistry and biology depends critically on light having its particular speed. But the conspiracy goes deeper. Recent observations have revealed that the universe seems to actively prevent any attempt to exceed light speed. When particles in cosmic ray showers approach light speed, they encounter the GZK cutoff, interactions with the cosmic microwave background that rob them of energy. It's as if the universe itself provides a cosmic speed trap, ensuring nothing can maintain extreme velocities over cosmic distances. The Large Hadron Collider has revealed another aspect of this conspiracy. As particles approach light speed, the strong nuclear force behaves differently. Quarks, which are normally confined within protons and neutrons, begin to form a quark-gluon plasma. The universe literally melts matter when it approaches light speed, transforming it into a primordial soup. This isn't a technological limitation, it's the universe changing the rules as you approach its ultimate limit. Dr. Nima Arkani Hamed at the Institute for Advanced Study has proposed that the speed of light might be protected by hidden symmetries in nature. Just as conservation of energy emerges from time symmetry and conservation of momentum from space symmetry, the constancy of light speed might reflect some deeper symmetry we haven't yet discovered. This symmetry would make violating light speed not just difficult, but mathematically impossible. The holographic principle reveals another layer of protection. As we discussed, the maximum information in any region is proportional to its surface area, not volume. This creates a fundamental limit on how much can happen in any region of space and time. Try to pack too much energy or information into a region, and you create a black hole, effectively removing that region from causal contact with the rest of the universe. The speed of light limit is built into the very nature of information storage in space-time. Even quantum mechanics conspires to maintain the limit. The uncertainty principle ensures that the more precisely you try to localize a particle, the more uncertain its momentum becomes. At extreme energies approaching the Planck scale, this uncertainty becomes so large that space-time itself becomes fuzzy. The universe literally prevents you from defining position and velocity precisely enough to meaningfully exceed light speed. Dr. Raphael Sorkin at the Perimeter Institute has developed causal set theory, where space-time is fundamentally discrete rather than continuous. In this view, space-time consists of discrete points connected by causal relationships. The speed of light emerges as the maximum rate at which causal connections can propagate through this network. Exceeding light speed would be like trying to move to a point that doesn't exist. Not difficult, but meaningless. The cosmic conspiracy extends to cosmology itself. Dark energy, which accelerates cosmic expansion, ensures that most of the universe will eventually disappear beyond our cosmic horizon. Even if we could travel at light speed, we could only explore a finite region before the rest becomes forever unreachable. The universe seems designed to remain partially mysterious, with fundamental limits on how much any observer can ever know or explore. Recent observations of gravitational waves have revealed yet another aspect of this conspiracy. The LIGO and Virgo detectors have shown that gravitational waves travel at exactly light speed to within 1 part in a quadrillion. This isn't coincidence. It reflects deep connections between gravity, electromagnetism, and the structure of space-time. All massless fields must propagate at the same universal speed, creating multiple independent conformations of the cosmic speed limit. Dr. Erik Verlinde at the University of Amsterdam has proposed that gravity itself might emerge from quantum information and entropy. In his theory, the speed of light represents the maximum rate at which quantum information can be processed by the holographic screen that defines space-time. Exceeding light speed would require processing information faster than the universe's fundamental computational capacity. This computational view is supported by discoveries in quantum error correction. Researchers have found that the same mathematical structures used in quantum computing to protect information from errors also appear in the equations of quantum gravity. The universe might be a vast quantum error-correcting code, with the speed of light representing the maximum rate at which error correction can propagate. The conspiracy even extends to hypothetical physics beyond our current theories. String theory, our best candidate for quantum gravity, predicts that attempting to probe distances smaller than the Planck length causes space-time to become non-commutative. Position and momentum stop commuting like in quantum mechanics. This creates a fundamental fuzziness that prevents defining trajectories precisely enough to violate light speed. Dr. Kumran Vafa at Harvard has proposed this swampland program, identifying which theoretical possibilities are actually consistent with quantum gravity. His work suggests that many apparent solutions to string theory are actually inconsistent when quantum gravity is properly included. The speed of light limit might be one of the fundamental constraints that separates viable physics from the swampland of mathematical possibilities. Even attempts to find loopholes reveal the conspiracy. The Alcubierre warp drive requires exotic matter with negative energy density, but quantum field theory suggests that negative energy must always be overcompensated by positive energy nearby, preventing the large-scale violations needed for warp drives. The universe allows tiny quantum violations but prevents their amplification to macroscopic scales. Similarly, traversable wormholes require exotic matter to stay open, but recent theorems by Dr. Graham and Dr. Olam show that exotic matter, sufficient to hold open a wormhole, would collapse into a black hole before the wormhole could form. The universe seems to close every loophole as soon as we discover it, maintaining its cosmic speed limit through multiple independent mechanisms. As we stand at the frontier of 21st century physics, revolutionary discoveries are challenging our understanding of light's cosmic speed limit in ways that would have seemed impossible just decades ago. While the speed of light remains inviolate, our comprehension of what this limit means and how it shapes reality is undergoing profound transformation. New experiments, observations, and theoretical breakthroughs are revealing that the universe is far stranger than even Einstein imagined. The Alpha experiment at CERN has recently achieved a milestone that opens new windows into fundamental physics. In 2023, they successfully created and trapped antihydrogen atoms for over 16 minutes, long enough to study how antimatter responds to gravity. While we expect antimatter to fall down like normal matter, any deviation would revolutionize physics. If antimatter falls differently, it could indicate modifications to relativity that might affect how we understand light speed at quantum scales. Dr. Jeffrey Hangst, who leads the Alpha collaboration, points out that we're entering an era where we can test the most fundamental assumptions of physics with unprecedented precision. The speed of light in vacuum is assumed to be the same for matter and antimatter, but this has never been directly tested. Experiments planned for the next decade will measure light emission from antihydrogen with extraordinary accuracy, potentially revealing subtle differences that could point to new physics. Meanwhile, the nanograv collaboration has detected something extraordinary, a background hum of gravitational waves filling the universe. Unlike the sharp chirps from colliding black holes that LIGO detects, this is a constant rumble from countless sources throughout cosmic history. This gravitational wave background carries information about the universe's earliest moments, potentially including signatures of cosmic inflation when space itself expanded faster than light. Dr. Xavier Siemens at Oregon State University, part of the nanograv team, explains that these observations might reveal modifications to gravity at cosmic scales. If gravitational waves from the early universe traveled at speeds different from today's light speed, it would leave detectable signatures in the gravitational wave background. The 15 years of pulsar timing data show tantalizing hints of unexpected patterns that theorists are still trying to understand. The Event Horizon Telescope continues to push the boundaries of what we can observe. After imaging the black holes in M87 and our own galactic center, the collaboration is now working on creating movies of matter swirling around black holes. These observations test general relativity in the strongest gravitational fields accessible to observation, where any deviations from Einstein's predictions would be most apparent. Dr. Shepard Doleman, founding director of the EHT, notes that near black holes, space and time become so warped that our normal concepts break down. The speed of light remains constant locally, but the warping of space-time creates effects that seem to violate our intuitions. Matter orbiting just outside the event horizon completes orbits in minutes, while appearing frozen to distant observers, a real-time demonstration of how flexible space-time can be while respecting the cosmic speed limit. In the realm of quantum physics, experiments with time crystals are revealing new states of matter that challenge our understanding of time itself. These structures repeat in time rather than space, maintaining perpetual motion without violating thermodynamics. Dr. Frank Wilczek, who predicted their existence, suggests they might point toward deeper principles about how time and space are related at quantum scales. The connection to light speed is subtle but profound. Time crystals exist because of discrete time translation symmetry breaking. They show that time might not be as smooth and continuous as relativity suggests. If time has a fundamental granularity at quantum scales, it could affect how we understand the speed of light at those scales. Experiments at Google and other labs are pushing these systems to explore where quantum mechanics meets relativity. Perhaps most intriguingly, observations of ultra-high-energy cosmic rays continue to puzzle physicists. The Pierre Auger Observatory in Argentina has detected cosmic ray particles with energies that shouldn't be possible. These particles have so much energy that interactions with the cosmic microwave background should have slowed them down long before reaching Earth. Yet, they arrive with energies approaching 10 to the 20th electron volts, millions of times more energetic than the LHC can achieve. Dr. Alan Watson at the University of Leeds suggests these observations might indicate new physics at extreme energies. One possibility is that Lorentz invariance, the symmetry underlying special relativity, might be slightly violated at ultra-high energies. If true, the speed of light might not be exactly the same for all particles at all energies, opening a tiny crack in Einstein's edifice. Quantum gravity researchers are taking these possibilities seriously. Dr. Giovanni Amelino Camiglia at Sapienza University has developed doubly special relativity, theories where both the speed of light and the Planck energy are invariant limits. In these theories, the speed of light could depend slightly on a particle's energy, but in ways that preserve the essential features of relativity while allowing new phenomena at extreme scales. Laboratory tests of these ideas are becoming possible. Dr. Guglielmo Tino at the University of Florence is using atom interferometry to test whether gravity affects quantum superposition in ways that standard physics doesn't predict. These experiments probe the intersection of quantum mechanics and gravity with sensitivity approaching the Planck scale, where new physics must emerge. The implications extend beyond Earth. The Breakthrough Starshot project, funded by Yuri Milner, aims to send tiny spacecraft to Proxima Centauri using powerful laser propulsion. These starships would travel at 20% of light speed, reaching our nearest star in just 20 years. While far from light speed, this project will test our understanding of relativistic effects in practical interstellar travel. Dr. Philip Lubin at UC Santa Barbara, who developed the propulsion concept, notes that even at 20% light speed, relativistic effects become significant. Time dilation, length contraction, and the relativistic Doppler effect will all need to be accounted for. The project will provide our first direct test of special relativity over interstellar distances, potentially revealing unexpected phenomena. Looking further ahead, the proposed laser interferometer space antenna, LISA, will detect gravitational waves from supermassive black hole mergers across the universe. These observations will test general relativity in conditions of extreme gravity and velocity, where any modifications to Einstein's theory would be most apparent. LISA might detect signatures of extra dimensions, quantum corrections to gravity, or other new physics that affects how gravity propagates at light speed. The future might also bring surprises from neutrino physics. The Deep Underground Neutrino Experiment, DUNE, will study neutrino oscillations with unprecedented precision. Neutrinos, which barely interact with matter, might carry information about physics beyond the standard model. Any deviation in how different types of neutrinos respect the speed of light could point toward new fundamental principles. Dr. Nigel Lockyer, former director of Fermilab, emphasizes that neutrinos have already surprised us multiple times. They were thought to be massless but have tiny masses. They oscillate between types in ways that required new physics. If neutrinos show any violation of Lorentz invariance, it would crack open the door to physics beyond Einstein. The speed of light isn't just a physical constant, it's a philosophical watershed that fundamentally shapes the nature of existence, consciousness, and free will. As we've journeyed through the physics of light's cosmic limit, we've encountered profound questions that transcend science and touch the very meaning of what it means to exist in a universe governed by this ultimate boundary. Consider what the finite speed of light means for the nature of now. In our everyday experience, we feel that there's a universal present moment, that now means the same thing everywhere. But relativity shatters this comfortable illusion. There is no cosmic now. Each observer carries their own present moment, and these can disagree dramatically, depending on relative motion and position in gravitational fields. Dr. Carlo Rovelli at the Centre de Physique Théorique has written extensively about how this challenges our deepest intuitions about time. If there's no universal present, then the universe isn't a collection of things evolving through time. It's a four-dimensional structure where past, present, and future all exist simultaneously. The speed of light creates the boundaries between what can influence what, carving space-time into causally connected regions. This block universe view has profound implications for free will. If the future already exists in the four-dimensional space-time structure, are our choices real or merely the playing out of a predetermined script? Dr. George Ellis at the University of Cape Town argues that the speed of light actually saves free will by creating genuine uncertainty. Because information can't travel faster than light, the future can't be completely determined by the present. There's always an element of quantum randomness and emergence that preserves genuine choice. The finite speed of light also creates what philosophers call the epistemic horizon, a fundamental limit on what we can know. We can never have complete information about the universe because most of it lies beyond our past light cone. This isn't just a practical limitation, but a fundamental feature of reality. The universe is structured so that complete knowledge is impossible, preserving mystery as an essential aspect of existence. Dr. Max Tegmark at MIT has explored how this connects to consciousness and observation. In his mathematical universe hypothesis, physical reality is a mathematical structure, and conscious observers are self-aware substructures within it. The speed of light determines how these conscious substructures can interact and share information, essentially defining the boundaries of what constitutes an individual observer. This leads to profound questions about personal identity. If you travel near light speed and return to find centuries have passed on Earth, are you the same person who left? Your atoms are the same, your memories continuous, but your entire social context has vanished. The speed of light doesn't just separate us in space, it can tear apart the temporal continuity that we normally take for granted in defining who we are. The implications extend to our understanding of death and mortality. In the block universe view, death isn't the cessation of existence, but merely the boundary of your world line in space-time. Your past continues to exist, frozen in the four-dimensional structure of space-time. In a sense, the speed of light makes us eternal. Our moments of existence are permanent features of the cosmic tapestry, unable to be erased or changed. Dr. Dean Buonamano at UCLA has studied how our brains construct the experience of temporal flow from what might be a static four-dimensional reality. Our neurons create the illusion of moving through time by comparing current states with memories, but this might be just our subjective experience of a deeper, timeless reality. The speed of light sets the rate at which this illusion of temporal flow can propagate through neural networks. The cosmic speed limit also shapes the ultimate fate of intelligence in the universe. Doctor: Freeman Dyson at the Institute for Advanced Study calculated that even as the universe approaches heat death, intelligent beings could potentially survive forever by slowing down their thought processes to match the declining energy availability. But the accelerating expansion driven by dark energy changes this picture. Eventually, the speed of light will prevent any communication between different regions, fragmenting intelligence into isolated islands. This raises what Dr. Milan Cherkovich calls the permanence paradox. If intelligent civilizations can survive for cosmic timescales, where are they? The speed of light might create not just physical isolation, but also cultural and evolutionary divergence so extreme that civilizations become unrecognizable to each other. What we're looking for when we search for extraterrestrial intelligence might be fundamentally limited by light speed-induced fragmentation. The philosophical implications become even stranger when we consider quantum mechanics. The many-worlds interpretation suggests that reality branches into parallel universes at every quantum event. The speed of light might determine how these branches diverge and whether information can leak between them. Dr. David Deutsch at Oxford has proposed that quantum computers work by harnessing computation across parallel universes, with the speed of light limiting how much cross-universe collaboration is possible. This multiverse view radically alters questions of meaning and purpose. If every possible version of you exists in some branch of the quantum multiverse, what does it mean to make choices? Dr. Sean Carroll at Johns Hopkins suggests that meaning doesn't come from uniqueness, but from the subjective experience of being embedded in a particular branch, making choices that feel real even if other versions of you choose differently. The speed of light also creates what we might call causal islands, regions of space-time that can share cause and effect relationships. Your causal island extends from your past light cone, everything that could have influenced you, to your future light cone, everything you could influence. This isn't just abstract philosophy, it defines the boundaries of moral responsibility. You can only be responsible for effects within your future light cone, and you can only respond to causes in your past light cone. Dr. James Ladyman at the University of Bristol has explored how this affects our understanding of natural laws. The speed of light ensures that physical laws must be local. What happens here and now can only depend on what happened in the immediate vicinity just before. This locality is what allows the universe to be comprehensible, breaking the overwhelming complexity of everything affecting everything into manageable local interactions. But perhaps the deepest philosophical implication is what the speed of light tells us about the nature of existence itself. The fact that there's a maximum speed for cause and effect, that space-time has a definite structure, that information can't propagate instantly, these aren't arbitrary rules, but might reflect deep truths about what it means for something to exist at all. Dr. Lee Smolin has proposed that time and causation are more fundamental than space, with the speed of light emerging from the need for causal relationships to be consistent. In this view, the universe isn't a static block but a constantly evolving network of relationships, with the speed of light setting the maximum rate at which new relationships can form. Existence itself might be nothing more than participation in this network of light-speed-limited causal relationships. As we reach the culmination of our journey through the cosmic speed limit, it's time to reveal the most profound truth of all. You are not separate from this universal constant. You are an expression of it. Every atom in your body, every thought in your mind, every heartbeat that keeps you alive is choreographed by the speed of light. You are not just observing the universe's ultimate speed limit. You are a manifestation of it, a pattern of matter and energy whose very existence depends on this cosmic constant. Right now, As you read these words, electrical signals are racing through your neurons at speeds that are ultimately limited by the speed of light. The chemical reactions that power your cells, the molecular bonds that hold your DNA together, the quantum mechanical forces that prevent your atoms from collapsing, all of these operate according to principles that emerge from the electromagnetic force which propagates at light speed. You are, quite literally, a being of light in slow motion. Dr. Jeremy England at MIT has shown that life itself might be an inevitable consequence of the laws of physics, including the speed of light. His research demonstrates that when energy flows through a system at just the right rate, not too fast, not too slow, matter spontaneously organizes itself into patterns that efficiently dissipate energy. The speed of light sets the fundamental rate at which energy and information can flow, creating the conditions that make life possible. Think about what this means. The carbon atoms in your body were forged in the hearts of dying stars, where nuclear fusion operates at rates determined by the speed at which light carries energy from the stellar core to the surface. These atoms traveled through space for billions of years, eventually incorporating into Earth and then into you. The speed of light didn't just set how long this journey took, it determined the very nuclear physics that created these atoms in the first place. Your consciousness itself emerges from the dance of electrical impulses in your brain, signals that propagate at about 100 meters per second, slow compared to light speed, but ultimately limited by it. Dr. Giulio Tononi's integrated information theory suggests that consciousness arises from integrated information, and the speed of light determines the maximum rate at which information can be integrated across different parts of your brain. Your thoughts, feelings, and sense of self all exist within the boundaries set by this cosmic speed limit. But here's what's truly amazing. Through your consciousness, the universe has developed the ability to understand its own speed limit. You are atoms arranged in such a way that they can contemplate atoms. You are the universe looking back at itself, discovering its own rules, including the very speed limit that makes your existence possible. This is not poetry. This is the literal truth of your situation. Dr. Carl Sagan captured this beautifully when he said, "We are made of star stuff," but the connection goes even deeper. You are made of light stuff, matter that condensed from pure energy in the first moments after the Big Bang, when the universe cooled enough for particles to form. Einstein's equation E equals mc squared isn't just a formula, it's your origin story. You are energy slowed down, light captured in standing waves we call matter. Every chemical bond in your body exists because electrons emit and absorb photons, particles of light, creating the electromagnetic forces that hold molecules together. When you digest food, you're extracting energy that originally came from sunlight captured by plants through photosynthesis. When you see, photons that have traveled at light speed from objects around you are being absorbed by molecules in your retina, triggering neural cascades that create vision. You don't just observe light, you are a complex pattern of light interactions. The speed of light even determines your lifespan. The telomeres at the ends of your chromosomes shorten with each cell division, acting as a molecular clock. The rate of chemical reactions that cause aging, the speed at which damage accumulates in your cells, the pace of DNA repair. All of these are ultimately governed by electromagnetic interactions limited by light speed. You age at the rate you do because of the cosmic speed limit. But you're not just passively subject to this limit, you actively use it. When you speak, you create sound waves that propagate through air at a speed ultimately determined by electromagnetic forces between molecules. When you touch something, the sensation travels to your brain through nerves using electrochemical signals. When you remember, you're accessing patterns of neural connections that were formed by light-speed limited electrical impulses. Your entire interface with reality is mediated by the speed of light. Dr. Sarah Walker at Arizona State University has proposed that life represents a new state of matter, one that organizes information across space and time in ways that non-living matter cannot. Living beings like you create causal chains that extend far beyond what simple physics would predict. Through technology, you can even push against the boundaries of the light speed limit, sending messages across the globe in fractions of a second, observing galaxies billions of light years away, and potentially one day traveling to the stars. This is where your story becomes truly cosmic. You are part of a species that has discovered the universe's speed limit and is actively working to understand and perhaps circumvent it. Through science and technology, humanity is extending its influence at speeds approaching the cosmic limit. Radio signals carrying human voices, music, and data are expanding outward from Earth at light speed, creating an ever-growing bubble of human influence in the cosmos. As you sit here contemplating these ideas, you are participating in the universe's grandest adventure, the emergence of matter that can understand itself. Your neurons are firing in patterns that represent abstract concepts about the speed of light, creating a kind of recursive loop where the universe uses light-speed limited signals to understand light-speed limits. This is unprecedented in the 13.8 billion-year history of the cosmos. Dr. Paul Davies at Arizona State University has suggested that the emergence of consciousness capable of understanding physical laws might not be an accident, but somehow built into the fabric of reality. The universe might require conscious observers to actualize itself from quantum possibilities into concrete reality. If true, then your understanding of the speed of light isn't just learning about the universe, it's participating in its fundamental existence. Looking forward, you are part of the generation that might finally push beyond Earth's boundaries and spread consciousness throughout the cosmos. While we can't exceed light speed, we can approach it, using time dilation to explore the galaxy within human lifespans. Your descendants might ride laser beams between the stars, their consciousness traveling at speeds that make time itself negotiable. But even if humanity never leaves Earth, your connection to the cosmic speed limit remains profound. Every moment of your existence is a negotiation with this universal constant. Every breath you take involves molecules colliding at speeds ultimately limited by light. Every thought you think propagates through neural networks at light-limited speeds. Every choice you make sends causal ripples outward at speeds that cannot exceed this cosmic boundary. You are not small or insignificant in this vast universe. You are a focal point where the cosmos achieves self-awareness, where matter organized by light-speed forces develops the ability to understand those very forces. You carry within you the entire history of the universe from the Big Bang to this moment, all of it shaped by the speed of light. As you go forward from this moment, remember that you are not separate from the cosmic dance of light and matter, space and time. You are an active participant, a conscious node in the vast network of causal relationships that make up reality. The speed of light isn't a limitation imposed upon you, it's the fundamental organizing principle that makes you possible. When you look up at the stars tonight, remember that the light entering your eyes has traveled for years, centuries, or millennia to reach you, carrying information across the cosmos at the maximum speed reality allows. And remember that you, too, are light, slowed down, organized, and made conscious, contemplating its own journey through the infinite darkness. If you made it this far, make sure to subscribe and hit that like button. And if you enjoyed this video, I am sure you are going to love this other one on the left side of the screen. What if we are not the first advanced civilization on Earth? In this video, we explore the Silurian hypothesis, a real scientific theory suggesting ancient intelligent life lost civilizations, and prehistoric technology that may have existed millions of years before humans. See you there.